Okay, so final thing we need to learn today is about calculating the area underneath a polar curve. So this is a new topic. Area under polar curves. Okay, so if we do a warm-up for this, then let's consider the simplest polar curve. So and that would be this guy, right? It's just some particular radius. So let's call that radius, say capital R for all theta. Well, what do we find out then? So let's draw a picture. If we have this polar curve, it's just going to do just a circle of radius R, right? And if we want to figure out the angle of, if we want to figure out the area underneath some part of it, say this part, right? So suppose that we have that this angle here was angle theta. So from this line to this line was theta. And we want to figure out how much area there is in this slice. So it's a slice of the pizza, say. So what do we do? Well, if we think about it, so the total area, because this thing's got radius capital R. Total area is pi capital R squared, right? And we have 2 pi worth of radians around the circle, right? That's how many angles we have. And so this particular little piece right here, that would be the same area as if we just were from 0 to theta, right? If we just rotated things around so that this line was just on the positive real numbers. So then the total proportion of angles we have contained in this little piece is going to be theta over 2 pi. So this is how much angles we have inside this little piece right here. And this is the total area. Oh, so I've written makes no sense. I'll erase that. So total area is this. So area in the slice is the total area, which is pi capital R squared, times the proportion of angles we have, the ratio of angles we have inside the slice compared to the entire range of angles. So it's going to be theta over 2 pi, right? So this is the fraction in the slice. Cool. So that obviously is the same as what happens when we just divide through by pi. So this is how much area we have in this slice, right? Cool. So if we have a very simple polar curve, then we can figure out how much there is in any slice just in this way. All right, so in general, given polar curve r of theta, we want to find out how to figure out how much area there is in some particular part of it. So this could be our polar curve, whatever it's doing, something like this, say. Oops. Okay, I can do something like this. This could be our polar curve. It doesn't have to start where it ends. And we might want to know how much area there is between some angle like this and some angle like this. So this could be angle theta 0 and this could be angle theta 1, right? So how would we do this? Well, we would use the Riemann sum machine. So as I've said a number of times, there is a way to get every single formula in calculus, well, every single integral formula in calculus at least, and that is to use these basic principles that, one, calculus allows us to localize things on a very small scale by using this concept of differentiability, and then understand things on a very small scale, and then add them all back up together again using this concept of an integral. Right? An integral is this generalized addition. So these two things kind of like these perfect tools to understand things. You have these perfect weapons. You break it up into little pieces where it's very easy to understand, and you have a perfect tool to add them all back up together in. And that's what we do. We've done it already many times. If you see multivariable calculus, you'd see it over and over again. It's worth getting happy with how this goes. So let's do it. So this is our range of angles. So let delta of theta be theta 1 minus theta 0 over n. N is some large number we'll decide on later. I now understand there's a disadvantage to this particular choice of, and I wrote theta 1 and theta 2, which I don't mean to, I mean theta 1 minus theta 0. And actually let's change the angle and let's call it this. And then let's call phi 0 theta 0, and then let's let phi k plus 1 equal phi k plus delta of phi, for k is equal to 0, 1 up to n minus 1. And that cuts it up into lots of little slices. So let's draw one of these slices. So this is one of a slice. So that's, say, the angle phi of k, and then a very tiny additional guy here. We have this additional angle delta phi. And we're going to take this picture and we're going to blow it up, as we've done many times. So take this guy, take your microscope, and blow up this picture to this picture over here. So this is the picture over here. I made it a little bit thicker just for artistic impression. So this is the angle phi k, right? So this distance here, this is the same color. This distance here is of phi k, right? And the angle right here is delta of phi, right? And the actual polar curve is doing some kind of thing like this, whatever. But let's just imagine that we approximate it by just taking the circle of radius r of phi k. So the circle of radius r of phi k, it's going to go like this. And if we just calculate this thing, that's incredibly close to the thing we're trying to calculate. There's a little bit of error here, but it's absolutely negligible compared to the angle delta of phi k, right? So this thing right here, well, it's just this, it's just the example that we did before. It's a slice of angle delta of phi of a circle of radius r of phi k. So this area is r of phi k squared using this formula over 2 times delta of phi, right? Because on a very small scale, this thing looks very much like it's just not doing much. It's more like it's flat, and therefore this is a very good approximation to the actual area. This little tiny bit here is really, really small compared to delta of phi. It's a order of delta of phi squared. We can forget about it. So that is what we're going to do for our approximation. So for every k, then we're going to get a different expression, and we're going to add them all together. So total area is the sum, k equals 0 to n minus 1 of all of these expressions of phi k squared over 2 delta of phi. And this is a completely standard looking Riemann sum, right? You guys at this point should be going, hey, it's Riemann sum. I know what happens now. This thing is going to tend to an integral. So if we put the limit signs over this, so limit as n goes to infinity of this thing is just going to be the integral from the angle theta 0 to the angle theta 1 of phi squared over 2 d phi, and that's it. Easy, right? And notice in particular, if we just have this guy as constant, we recover this formula straight away, which is what we'd expect, right? This more general formula should recover the special case. And with this formula, then we can easily calculate the area underneath whatever slice of a polar curve we want, right? As in all of these cases, the actual calculation integral is something pretty straightforward. It is just knowing the formula, getting the formula right. So as I implore you every time, please draw these pictures for yourself. Convince yourself that this is the reasonable expression. This is the correct thing to give the general area underneath a polar curve over some range of angles. Once you're convinced of this, answering these questions won't be hard, and we'll practice some examples next time. Okay, that's it.